Okay, interruption, but we'll continue on. So we've got everything here, so we can plug in. We got the square root, and we got, let's use some parentheses here. 3 times 8.314 times 300.15 divided by 0.3032. What happened? Okay. Let's start over. Square root of 3 times 8.314 times 300.15 divided by 0.032. 32. Yes. All right. 483.7. Everything is in good standard units, so this is going to be meters per second then. So 484 meters per second. All right. Continuing on. So I put a lot of problems here, a lot of samples here for you to have practice. Of course, your real test won't be this long. Part F, find the pressure of certain, so this is a volume of moles, this is N, and this is T in Celsius, and we want P. So this looks like a ideal gas law problem. Excuse me, PV equals nRT, and we need our T in Kelvin though, so T in Kelvin is T Celsius plus 273.1, excuse me, 15, so we got 283.15 Kelvin. And we're looking for P, so just rearrange this. We got P equals nRT over V. V is in good units, N is good units. Oh, excuse me. So we've got 10 times R, 8.314 joules per mole Kelvin. And this is moles. And T is 283.15 Kelvin over 0.2 cubic meters. Everything's good units, so we got 10 times 314. Looks like 117.7. PA 118 pascals. Whoops. Oh, there's a 3 there. Missed a little factor of 3 kilopascals. And divided by a small number here. Alrighty. Gotta watch that. Okay, next part. Part G. Find the change in length of a 2 meter long copper wire if its temperature goes from 25 to 80. Assume the coefficient of linear expansion for copper is this. So this is what we call alpha. We got delta T information here. We've got an original length. We call that L0, L0. And so our linear expansion formula was delta L equals alpha L0 delta T. And so we got, this is per degree Celsius. Our alpha is given as, so that's all cool here. And so we got 16 times 10 to the negative 6. This is meter per meter, so it really cancels out. So it's 1 over degree Celsius. And then L0 is 2 meters. And then delta T is final minus initial, goes from 25 to 80, so it's 80 minus 25. That's all Celsius. Alright, so Celsius cancels, and we're going to end up with meters, which is what we're looking for. So 16 negative 6 times 2 times Oh, let's just have the calculator do it. 80 minus 25. 1.76 10 to the negative 3 meters. 1.76 millimeters. Is that what I got before? Looks like that's what I got before. Good. Alright. Got some stuff kind of flowing around here. So this is latent heat diffusion of water. Put it all over on that side. Alright. We're going to have these numbers given. We want to find the heat needed to raise the temperature of 5 kilograms of water 20 degrees. So it says water, we're going to assume it's liquid water, and it's just all liquid water. So we're going to say Q then is mass times specific heat times the change in temperature. This raised at 20 degrees, so that's going to be delta T is given. Of course, this is the mass. And specific heat of water is given here. So we're just going to plug stuff in. 5 kilograms times specific heat of water, 4186 joules per kilogram Kelvin. And delta T is 20 degrees Celsius, which a degree Celsius in the delta T's and the step size, delta C and delta K are the same, so we're all right here. So that's all we need. Let's plug it in. $41.86. Yes. 418,600. And what is this? Is these cancel out, kilograms cancel out, and we got joules. That's good. Looks like kilojoules to me. 419 kilojoules. All right, part B. Find the specific heat of 5 kilograms of material that took so much Q of heat. This is so many joules of heat, so that's going to be Q. And had a temperature increase, so this is a delta T. Assume the material is isolated, had no heat loss. So this is the ideal case. All the heat went into the material, so we can use it to calculate the specific heat. So we got C, let's do Q equals M, C, whatever the material is, delta T. And so C is what we're looking for. Divide through by the things that are multiplying C, so we got Q divided by M delta T. Q is 3,000 joules. M is 5 kilograms. Delta T was 50 degrees Celsius. All right. 3,000 divided by 5 times 50. 12. Okay. 12 watts. 12 joules per kilogram degree Celsius. 12 joules per kilogram degree Celsius, or Kelvin, whichever one. Alrighty. Part C. Find the heat needed to change 4 kilograms of ice at -5 to water at +5. So this is going to be needing a bit of room. Hopefully we can get in here. So we've got actually 3 stages, right? So we're going to go, the ice has to get to 0. So we're going to do Q from 0, or from -5 to 0 is going to be MC of ice times delta T. All right, and then we're going to have Q to freeze. To thaw. We're going the other way. To thaw is going to be the mass times the latent heat diffusion of water. Right, and then we're going to have Q to go, and that's not going to change the temperature. It's still going to be 0. Now it's just going to be water instead of ice. And then we want to go 0 to 5. Again, we're going to do mass times C, but this time it's C of water times its delta T. Right? And so we're going to add up all of these in the end, add them all up to get our Q total, to go all the way from -5 to +5. Okay, so let's get working here. So we've got M is 4 kilograms, C of ice, 2100. joules per kilogram Kelvin, and the delta T is -5 to 0, so that ends up being 5 warmer, +5. All right, so we're going to get a Q there of 4 times 2100 times 5. 42 kilojoules. 42,000 joules, whichever. Okay. To go to thaw, can't read this, but it says thaw. The heat needed to thaw the thing is going to be, again, the mass, 4 kilograms. And now we need a latent heat of fusion. Fusion, it'd be like coming together or uncoming together, same thing. So latent heat of fusion of water, 333 kilojoules per kilogram. All right, so 4 times 333, 1332 kilojoules. Let's get them all in the same kind of looking unit. So put 3 zeros on there. All right, so now we got up to 0. We melted it. Now we've got to get it from 0 to 5. All right, so now it's water. So we're going to have 4 kilograms. But now we got C for water. So 4186 joules per kilogram Kelvin times a change. And we're still increasing, but we're going from 0 to 5, so it's going to be a +5 degrees Celsius. All right, so multiply that out. 4 times 4186 times 5. And this is in joules. So 83,720. All right, joules. So we got to add those all up. Add these 3 all up to get the Q total. 42,000 plus 133,2,000 plus 83,720. Okay, 1457720. Okay, so 1.46 times 10 to the 6th joules, so megajoules, 1.46 megajoules. Alrighty, that's a lot of joules. Trying to check my work here, can't find it. 3C. Okay, we've got different numbers. Yeah, I accidentally put 5 kilograms instead of 4 kilograms. So again, my solution I gave you before is wrong. I think these numbers are right. We'll keep on going. Find the final heat of a 1 kilogram silver teapot, originally at 25, after it is filled with 1 kilogram of tea. That's 100 degrees Celsius. Assume no heat is lost, and the tea and teapot are at the same temperature in the final condition. Okay, so we've got hot tea, and it's going into a cooler teapot, and so it's going to give heat to the teapot, and then they're both going to be at the same temperature. So we're going to have the Q of the, I have it written as water, but anyway, Q of the tea plus Q of the teapot is going to equal 0, right? So the total heat is the same, it just gets passed around between the two, all right? And so Q of the tea is going to be MC of T Okay. This one is a little bit. All right. MC of the T times delta T of the T plus MC of the pot, teapot, times delta T of the teapot. And we're going to have to make an assumption. I didn't give you C for teapot, or for T, so we're going to just assume T is water. All right. C, so we're going to assume C sub T equals C of water. All right. Oh well. And we got M of T, M of, okay, teapot. They're both the same. So let's keep going here. So we've got, let's put in, should we put in numbers? Nah, let's keep going. So mass of the teapot, I'm just going to go for T and TP. So times C of water. Temperature of the teapot is going to end up at some temperature T that they both have, and it's starting at the T. This is the T, 100 degrees Celsius. And then we've got the mass of the teapot times C of silver. And then it's going to also end at the same temperature T, but it's starting at 25. All right, I need more room. So let's just give ourselves a little spot up here. So both of the M's are 1, so they're going to kind of disappear. And so we're going to have, multiply this out. So the C of water, C sub water, 4186 joules per mole Kelvin. And the C of silver, (230) joules per mole Kelvin. All right. So here we'll have 4186 times T minus 4186 times 100. I don't know why I'm doing this, but anyway, add 2 zeros. 418600 plus silver times T, so it's 230 times T minus silver times 25, so that was a 230 times 25. 5750. That equals 0. And so adding up these, bring that to the, add those together, bring to the other side. So we're going to have T is equal to 48,600 plus 5750 all divided by 4186 plus 230. Oh, okay. 48,600 plus 5750. All of that together divided by 4186 plus 230. .31 Kelvin. This is final heat. It should be temperature. T final. 12.3 Kelvin. So 12.3 Kelvin. Not Kelvin. We didn't change to Kelvin. Should be C. These were C's. And so if these are C's, then T is going to be in C also, so that we're 12 Kelvin. That's terrible cold. Okay. Does this make any sense? No, it doesn't. What did I do wrong? Okay. 41. So they should be, the heat of the two together should be somewhere in between the heat we started with. 4160, 5750. Oh, I lost a 1. 418,600. 41860. That looks better. There we go. Whew, okay. 96.09 degrees Celsius. So 96.1 degrees Celsius. Makes much more sense. All right. So the water has a high specific heat. It's not going to change temperature very much. Teapot's going to change quite a lot. The teapot started at 25 and the water started at 100. So the answer is in between the two. I like it much better than 12. Looks good. All right. Find the power needed to heat 2 kilograms of water from 25 to 100 in 5 minutes. So power is energy or work over time. Our energy here is heat, so we're going to be having Q over time. 5T is 5 minutes. We want seconds. For power, it's joules per second, so we're going to multiply by 1 minute is 60 seconds. So we got 300 seconds for T, and Q is, everything is just water, MC water, delta T, 2 kilograms, C of water is 4186 joules per mole Kelvin, kilogram Kelvin, and delta T is 75 degrees. 100 minus 25. Okay, so let's get Q here in a minute. So we got 2 times 4186 times 75. 627,900. Okay, so plugging into a power equation then, 627,900 divided by 300. 2093 watts, 2.09 kilowatts. Alrighty. Moving on to number 4. Consider a simple harmonic mass system made of an ideal horizontal spring with a 1.4 kilogram mass attached. Assume the spring constant is 450 newtons per meter and the mass is pulled back to a maximum of 30 centimeters to start the motion. Draw a free body diagram for the mass. So we got the mass, it's always got gravity. It's going to have a normal force because it's sitting on a surface. And then the interesting one that's causing stuff to happen is the force of the spring. Possibly could have force of friction, but since it's a simple harmonic system, we're going to assume no losses, no friction. Okay, what is the maximum PE of the spring? So potential energy is 1/2 kx squared. We want the max, so PE max will be when we have max x. X max is A, maximum displacement, and we're given that it's 30 centimeters. This is A, so it's 0.30 meters. So P max is 1/2, and we got K here. The spring constant is K, so 1/2 times 450 newtons per meter times 0.30 meters squared. .25 joules, so PE max equals 20.3 joules. What will the speed be when the mass crosses the spring's relaxed position? So And the mass is going to be going back and forth, and we'll have x equals 0 position in the middle, and that's the V max position as well. Maximum velocity and maximum kinetic energy when we have 0 potential energy, when it's in the middle, so x is 0. So we have 0 potential energy. Okay, so, and we also just have the formula that we gave you, so we can just use that. V max is the square root of a k over m, and so that's 0.3 times the square root of 450 over the mass, 1.4 kilograms. Newton per meter, meters, everything is good. .379 meters per second. 38 meters per second. Continuing on, how long will it take for the mass to return to release point after one oscillation? So this is just, so the mass goes all the way in and then comes all the way back to where it was released, and it just keeps going back and forth and making a sine wave, right? And so the maximum, we're looking for the distance between the two maximums when this is versus time. And so this is the period, what we call a period for one oscillation. And so, I guess I should check my numbers, but okay. Oh, my numbers were bad, so yeah, new numbers. Let's look at the period. We have several different ways of looking at the equation. Period is 1 over the frequency, which is, frequency is omega over 2 pi, so omega equals 2 pi f, and so f equals omega over 2 pi, and so 1 over f is 2 pi over omega. Again, however you have them on your equation sheet, 2 pi over omega, and just from the simple harmonic motion equations, we know omega is either g over L for a pendulum, or square root of g over L, or square root of k over m for a mass. Alright, and so we end up with the square root of m over k. Did I do it right? Yes. 2 pi square root of m over k, just flipping the fraction from the bottom inside the square root. So 2 pi square root of m 1.4 kilograms over k 450 Newton per meter. So the period, Newton is a kilogram meter per second, so that's how we're going to get seconds to appear here. So 2 times pi times square root 1.4 divided by 450. 0.3505 seconds. So t equals 0.351 seconds. Okay. And then find the speed of the mass when it is 20 centimeters from the spring's relaxed position. Alright, so we're going to have, KE of some condition plus PE. It's an ideal, of the same position, KE2 plus PE2. Since we have no losses, the simple harmonic motion is assuming an ideal kind of case where we have no losses. So we have conservation of mechanical energy, KE and PE. Let's just use the case here at max PE, because we calculated that a minute ago, 20.3 joules. So we're going to do this condition where kinetic energy is 0, it's all PE, so PE max, which is 20.3 joules. Yes. is going to be equal to KE2 plus PE2. And so this one will be the condition 2 will be this condition. So KE is in general 1/2 mv squared, so 1/2 mv2 squared plus potential energy, it's just from the spring, 1/2 kx2 squared. All right, and so plugging in for that, we have 1/2 m is the 1.4 velocity, that's what we're looking for, v2 squared plus 1/2 k is 450 Newton per meter, and x we're given 0.2 meters squared. Okay, so solve that for v2 is going to be square root of this side 20.3 minus all this minus 1/2 450.2 squared, and then divided by what's multiplying v, divided by 1/2 of 1.4. All right. Oops. We'll see if we can do this. So square root of, on the top, 20.3 minus 0.5 times 450 times 0.2 squared. And then we're going to divide that by, let's use some parentheses, 0.5 times 1.4. Does that look good? I think so. 0.018 meters per second. So we'll just say V2 equals 4.02 meters per second. Okay. Yeah, I had problems with that before, so hopefully that's the right answer. Okay, number 5. Consider a waterproof guitar, anyway, with 0.8 meter length of strings for the strings to vibrate. Assume the strings have 2 grams per mass, 2 grams per meter mass per unit length, and assume that the high E string has a frequency of 330 while low E has a frequency of 82. Use the speed of sound is 330 and the speed of sound in air is 330 and the speed of sound in water is 1500 meters per second. What are the wavelengths of the strings vibrations of the two different E strings? Alright, so guitar has 6 strings, and the 2 outer ones, the fattest and the skinniest, anyway, the biggest and the smallest are both E's. So we're just kind of assuming they're all the same grams per meter, which is probably not right, but we're going with it. Okay, so we need to find the wavelength. So remember, for the fundamental frequency, or well, for the fundamental frequency, when we have a string vibrating, it's going something like this between the 2 ends. This is half a wavelength, so L is equal to excuse me, lambda over 2, and so lambda is equal to 2L. And that's the same for both of the strings. And so it just has to do with the how long the guitar is, basically. So lambda is equal to 2L is equal to 2 times the vibrating part, 0.8 meters, and so it's equal to 1.6 meters is lambda for low E and lambda for high E. Right, because it doesn't depend on the frequency. It depends on how the guitar is made. All right, so, or the length of the string. So what are the velocities of the 2 different E strings at their fundamental frequency? So now the velocity, right, are going to be different because they're vibrating and making different frequencies. And so now we're going to use the frequency. The fundamental frequency is velocity over wavelength, which is 2L. All right, and so velocity equals 2L times the fundamental frequency. And so velocity of the low E is going to be 2 times L, 0.8 meters, times frequency of the low string at 82 hertz. So it's meters per second, so 2 times 0.8 times 82, 131.2 meters per second. So V low E, 131 meters per second. Same formula for high E, except for just a different frequency. So V high E is still 2 meters long. No, 2 is just a factor of 2, 0.8 meters long. And now the frequency is 330 hertz. Okay, 2 times 0.8 times 330. Coincidence that it comes out to be the same as the speed of sound. I believe 528 meters per second is V low, high E. Alright, so hopefully that makes a lot of sense. High frequency sounds take high speed vibrations. Low frequency sounds, lower speed vibrations. Okay. Part C, find the tensions needed for each string to be tuned to the correct frequency. Alright, so how do we get them to make these different sounds? You turn the little tuning knobs to get them to be in tune. So we got the general formula: velocity of a string is the square root of the force of tension divided by mass per unit length. Being careful of the units. So velocity of the low E going to be, well, let's rearrange. So we're looking for the tensions needed. So let's solve this for f of t then. Square both sides, so it's going to be v string squared. And then multiply through by what's dividing here, mass per unit length. Alright, so force of tension of the low E is going to be mass per unit length, which is 2 grams per meter. We want it in kilograms, so 0.002 kilograms per meter times velocity of the low E string, 131.2 meters per second squared. So force for the low E, 0.002 times 131.2 squared, 34.4 newtons. And same thing for the high E, force of tension for high E, same mass per unit length, although in reality they're probably fatter strings, but we're going with this. And then times the velocity squared here, 528. Okay. Let's go 558 newtons. Ooh, those seem high. Anyway, we'll go with it. Okay. Continued on the next page. So, continuing with the same problem on the next page. What is the wavelength of sound from the high E string if it travels in air? Wavelength of sound from the wavelength of the sound wave from the high E string. So now we've got the wavelength in air. So we've got V equals lambda F, but now the V is the velocity of sound in air, right? Not the string anymore. The other ones were the velocity of the string, but now it's in the air. So we want the wavelength, and so this is also the wavelength of the sound. I guess we should say the velocity of the sound. Okay, not the string anymore. And so we've got lambda equals V over F. This is all for the sound. This is for the high E. That's all. We're not doing low E in this case, so that's good. Okay, so velocity of sound in air is what this is. So that's a 330 meters per second. Not the string anymore, it's the sound. And the frequency is frequency of the sound. For the high E, it was also 330. Okay. 30 hertz, 1 over seconds. And so we're going to end up with just 1. Yep. 1. This hertz is 1 over seconds over, and the meters per second, so it's just going to be 1 meter is lambda of sound for the high E. Interesting. Okay. What is the wavelength of the sound from the high E string if it travels in water? All right, so now we need velocity of sound in water instead equals lambda F. And so lambda, again, wavelength of the sound in water is the velocity of the sound in water, which was 1,500 meters per second, and then the frequency is still 330 hertz. .55 meters. Lambda of sound, water. So is air. Okay, so this is maybe a little confusing and doesn't really oops, did I do something wrong? It looks like I got the answer wrong again in the solution key. I had a decimal point off, so I think this is right though. 1,500. Let me double check my velocity of sound in water. Yes, 1,500. Okay, so again, answer key is wrong. The original answer key is wrong. 4.55. Yes. Okay. On to number 6. Consider we got a volume here. That's a capital V. 30 cubic meter sealed room with a certain mass of air acting as an ideal gas. Assume the air is 21% oxygen, 79 nitrogen. We got our MAs for those. So what is the effective molar mass of the air? So this is a mixture of two things, and so we'll have molar mass of air is going to be 20% or 21%, 0.21 times O2, and this should be, okay, this should really be 32. I screwed up. So 0.032 kilograms per mole, plus for the nitrogen it is 79%, so 0.79 times 28, well, 0.028 kilograms per mole. Okay, so we got 0.21 times 0.032 plus 0.79 times 0.028, and so we get 28.84 kilograms per mole. So MA air 28.8 kilograms. Grams per mole. Sorry, grams per mole. Or 0.0288 kilograms per mole. Okay, did I get that one wrong or? Yep, I just didn't get it corrected in my on the answer sheet here, or on the question sheet there, but I did it right. You used 32 in my key before. Okay, how many moles of air are in the room? All right, so we've got number of moles is going to be however much mass we have divided by how much mass is in 1 mole. Okay, and this is for the air. And so we have 39 kilograms divided by 0.02884 kilograms per mole. All right, so the kilograms cancel. We're going to have 1 over mole on the bottom, so we end up with moles. So 39 divided by 0.02884. 1, 3, 5, 2. Yes. Moles. 1352 moles. Good. Or 1350 if we're rounding, getting lazy here. That should be the official answer, I guess. If the room is at standard atmospheric pressure, what is the temperature? Alright, so we're getting to the PV equals nRT kind of thing happening here now. And so standard atmospheric pressure is 1 atmosphere, which is 101.3 kilopascals. And we want to know the temperature, so let's rearrange this for temperature. T is PV over nR. P, we just said 101.3 kilopascals. Volume of the room, 30 cubic meters. N is the moles, we just got 1352 moles. And R is a constant, 8.314 joules per mole Kelvin. Alright, plug those in, 101.3 times 10 to the third for the kilo times 30 divided by, some parentheses, 1352 times 8.314. 270.4 Kelvin. T 270 Kelvin. It didn't ask for it in Celsius, so I guess Kelvin is fine. Sure. Okay. What is the pressure if the temperature increases by 10 degrees Celsius? Alright, so now the temperature becomes 290 Kelvin. 10 degrees. Let's add 10. 280 Kelvin. And we're looking for the pressure. So rearrange this. So we're going to give P is nRT over V. We could probably do some ratio stuff, but let's just plug it in. 1352, 8.314. 1352 mole, joule per mole Kelvin. T is 280 Kelvin. Volume is 30 cubic meters. Kilopascals. So P equals 105 kilopascals. Good. If the specific heat of air at a constant volume is 0.72 kilojoules per kilogram Kelvin, how much heat is needed to cause this temperature increase? So we're kind of mixing things here, going into the heat kind of stuff where we got M, C, delta T. And so how much mass of air did we have? 39 kilograms. C was just given as 0.72 kilojoules per kilogram kelvins, and the delta T is 10 Kelvin, because kelvins are the same size as Celsius degrees. And so we're going to end up with kilojoules, 39 times 0.72 times 10. So Q equals 281 kilojoules. What is the total internal energy of the air in the room after the temperature increase? So we've got our KE total is, we got a couple formulas for it, but we don't have capital N, we have little n, so let's use the 3 halves in our T version. Double check. Yep, okay. And so we got 3 halves, 1.5, N was 1352 moles. R 8.314 joules per mole Kelvin, and T is the new temperature, 280 Kelvin. Okay, so the total kinetic energy is 1.5 times 1352 times 8.314 times 280. 4.72 times 10 to the 6th megajoules. Okay. Good. Number 7. I'm gonna probably have to pause here to go to class, but we'll do a little bit here. Consider a pan full of water with density 100 or 1,000 kilograms per cubic meter at 20 degrees. We got the dimensions of the pan. We got C of lots of things. Kilogram Kelvin kind of went to the other side, and we've got the latent heats of fusion and vaporization. So what is the mass of the water? Mass equals density times volume. We need the volume. We've got a circular cylinder kind of thing. R equals 0.08 meters. The height is 0.1 meters. So pi r squared times h is pi times 0.08 squared times 0.1. So the volume is 2.011 times 10 to the negative 3 cubic meters. These are all meters, yes. Okay, so that's good. And so then the density is in kilograms per cubic meter. So we get kilograms. So M equals, I got a 10 to the negative 3 here. 10 to the negative 3, 10 to the positive 3, cancel out, so we just get 2.011 kilograms. 2.01 official answer. How much energy would it take to get the water to be steam at 100 degrees Celsius? Okay, so we're going all the way to steam. So we're going to have two parts. We're going to have Q to get from 20 to 100 degrees, right? It's just M, C of water, delta T. And then we're going to have Q to evaporate. going to be M times the latent heat of vaporization for water. We're going to have to add those together to get Q total. Alright, so we got M, 2.011 kilograms. We got water, specific heat of water, 4186 joules per kilogram Kelvin. And we got the temperature change. The first one is 100 minus 20, final minus initial. And so let's just do that. 2.011, 4186 times 80. 400 joules. Okay, and this one again, same mass, latent heat of vaporization, 2260 kilojoules per kilogram. 2.011 times 2260. Time to go to class. Let's finish this up real quick. 4.5. Well, let's just, so 4.5 times 10 to the third, so 4.545 times 10 to the third joules. Yes. So let's add these up. 673,400 plus 4,545. So Q total is 5218400 joules. Q total 5.22 megajoules. Okay. All right, we better stop there so I can get to class.